All right, so this is the second part of section 9.8, and this second set of directions says factoring polynomials completely. Remember on the quiz I said that that word completely is talking about the fact that there's a greatest common factor. It's also talking about the fact that there might be a greatest common factor, or once I pull out that greatest common factor, there might be another polynomial that can factor again. So let's look at that first example. In number 1, 42x to the third minus 30x squared. Well, the x squared stands out, and 42 and 30, the biggest number they're both divisible by is 6. So 6x squared is my greatest common factor. I start my parentheses, and this time I end up with 7x minus 5, and close my parentheses. So that this problem is only a GCF problem. In number 2, however, we go through that same process. 9 and 4 do not have any common factors other than 1. D to the fourth and d squared, they have d squared in common. So I have my d squared. I start my parentheses, and I'm left with 9d squared minus 4. This 9d squared minus 4 is factorable. It happens to be a difference of perfect squares. 9d squared is made up from 3d times 3d. And negative 4 is a perfect square. It could be positive 2 times negative 2. So that I end up with a plus, minus, or conjugates, and a GCF. So I needed to make sure I have all 3 of these factors in my answer. Let's look at number 3. There's a leading negative, so we need to make sure we pull out a negative. 8 and 2 have a common factor of 2, and there is a single p being shared. When I do my GCF, negative 2 times positive 4, p times p squared, plus, because I factored out that negative, and 2p, well, that would be a 1. We need to be able to identify that 4p squared plus 1 is not factorable. It's a sum of perfect squares, and that is not a special case, so we can stop. Number 4 has a GCF of 2, so we end up with m squared plus 16m plus 60. And now that I have my GCF of 2, I can factor this trinomial. Is there a pair of numbers that multiply to positive 60 and add to 16? Hopefully you've got it. M plus 10 times m plus 6. So things that we've seen. We saw that we could pull out a GCF, and that's all we could do because we would then have a normal binomial in our quantity. In question number 2, we factored out our GCF, and in our quantity, we now had a difference of perfect squares, and we could factor that quantity using our shortcut. They're conjugates, 3d plus 2, 3d minus 2, and that GCF just tags along in the front. In number 3, when we pulled out that greatest common factor, we saw a situation where there's a negative. We pulled that out, and when we had the quantity in here, we saw that we had a sum of perfect squares, and that is not factorable. That might be a good thing to jot down. I think I'm going to. All right, 5 and 6 are 2 for you to try on your own. Hopefully you tried them, and hopefully you came back and checked your work and you see that you've done them correctly, because they were both problems like number 4. Because number 4 is the most common version that we see. All right, the last piece then are the solving problems. And I know we've already seen this at least a little bit. Let's go ahead and work through number 1 together. Greatest common factor is 6. When I factor out my 6, I'm left with 2x squared plus 3x plus 1 equal to 0. That 0 is pretty important. Now I need to factor my trinomial. My 6 is just going to tag along at the beginning here. So that, oh, maybe I want to use an x in a box. Maybe you don't need one. Again, using that factoring scale, however you get to 2x plus 1 times x plus 1, an x in a box, we use FOIL, smiles to check, an x in smiles, whatever version you're using. And then we simply say each factor equal to 0. So 6 equal to 0, well, that can't happen, so that's a pointless step. Not always pointless, but in this one, it just doesn't do us any good. 2x plus 1 equal to 0. Subtract 1. Divide by 2. So x equal to negative 1/2 is our first legitimate answer. And then we need to finish up x plus 1 equal to 0. All right, give problem number 2 a try. Again, I think I said it clearly, but maybe I didn't, that this factoring step, you might have used an x in a box, and that is just fine if you had done that, whatever method you're using for factoring. But try number 2, and while you're at it, why don't you try number 3 as well? So 2 and 3, give them a try. All right, so these were the problems where we had a GCF that factored out, and we were able to factor again. I would like to work through number 4 together before I let you try one of this type on your own. Remember, it's still a solving problem, so we need to make it equal to equal to 0 first. So in this particular problem, we have to add 30x to both sides. Descending powers of x. And now we're going to do a GCF step. What do they have in common? 5, 25, and 30. Well, they're all divisible by 5, or they're all multiples of 5. X to the third, x squared, x. I'll share at least one x. What's left when I undistribute or factor it out? X squared minus 5x plus 6, still equal to 0. Now we have to factor this trinomial, but that GCF, that 5x, needs to tag along. And to multiply to a positive but add to a negative, they're both subtractions. So in this case, minus 3 minus 2. X minus 2 equal to 0. Now that we have multiplication, we can take each factor and set it equal to 0. So 5x equal to 0, x minus 3 equal to 0, and x minus 2 equal to 0. So my 3 answers, divide by 5, I get x equal to 0. There's my first one. Add 3 to both sides, x equal to 3 is my second. And add 2 to both sides, x is equal to 2 is my third answer. Remember that the degree of the polynomial will tell you how many answers to expect. So this was a degree of 3. I expected 3 answers. Would you please give problem 5 and problem 6 a try? In problem 6, remember to undistribute that negative 2, because leaving negative never stays. I'm fairly confident that you did well on these. Just remember the 2 things that we learned today. We talked about factor by grouping, and we talked about factor completely being not just GCF, but potentially pull out a GCF and factor again. Good luck, and I will see you in class.